An experiment is a process with well-defined outcomes. A sample space is a list of all possible outcomes for an experiment. Let's consider the process of rolling 2 dice. It would be considered an experiment because the outcomes are well defined. Each dice could land with the 1 through 6 spots facing up. So if we were to list the sample space for this experiment, what we would have is a 1 and a 1, a 1 and a 2, a 1 and a 3, and on out to a 1 and a 6, a 2 and a 1, a 2 and a 2, a 2 and a 3, and on out to a 2 and a 6. And this pattern could continue until we had a 6 and a 1, a 6 and a 2, a 6 and a 3, and on out to a 6 and a 6. There would be 36 equally likely outcomes. Each of these outcomes would be as likely to occur as any other with a balanced set of dice. A classical probability is defined by dividing the number of favorable outcomes from an experiment by the number of equally likely outcomes. This notation here, P of E, just means the probability that some event E might occur. An event is a collection of outcomes. So let's consider the event rolling a sum of 7 when we roll 2 dice. So this event would be a collection of outcomes from the sample space, and that collection would consist of a 1 and a 6, a 6 and a 1, a 5 and a 2, a 2 and a 5, a 4 and a 3, and a 3 and a 4. So there are 6 favorable outcomes, and there are 36 equally likely outcomes. So that probability would be 36ths or 1/6. This could also be noted in its decimal form as 0.16 repeating, and then it might be rounded to whatever would be appropriate for the given situation. Empirical probabilities are calculated from observations. Suppose, for instance, we have a class that has 8 seniors, 4 juniors, 3 sophomores, and 5 freshmen. This would give us a total of 20 students. So we would estimate then from this group that the probability that a junior would be selected from a group of students at this university would be 4 out of 20, or 1/5, or 0.20. Whenever we encounter the word "or" when talking about probabilities, we automatically have to think addition. The addition rule will apply. Here the addition rule states that the probability that events A or B will occur is equal to the probability that event A would occur plus the probability that event B would occur minus the probability that events A and B would both occur. Now we can see what this is referring to if we look at what's called a Venn diagram. And in a Venn diagram, we would have a universal set, and then we'd have a couple of sets that are contained inside this set. And here we're going to call them sets A and B. Now, if we were to add sets A and B together, what would happen is this little intersection area here would get added twice. So in order for it to be in that sum only once, we'd have to subtract it back out once. This is where the addition rule comes in. Let's suppose that we are going to draw one card from a standard deck, and we want to find the probability that we would draw a 6 or a heart. Now, using this addition rule, this would be the probability that we would draw a 6 plus the probability that we would draw a heart. But then we have to think about the fact that there is a card that is both a 6 and a heart. It is the 6 of hearts. So we have to subtract off the probability that both events would occur at the same time. The probability that we would draw a 6 and a heart. There are 4 6s out of 52 cards. There are 13 hearts out of 52 cards. But of those 4 6s, one of them is the 6 of hearts, and of those 13 hearts, one of them is the 6 of hearts. So it's in there twice, so we have to subtract it out once. There is one card that is both a 6 and a heart, so here is its favorable, and then divided by 52, the number of equally likely outcomes. So this probability will be 16 out of 52, which could be reduced to 4/13. Whenever two events cannot occur at the same time, then they are called mutually exclusive events. And we can see in this Venn diagram that these two sets, A and B, do not intersect. So there's no need to subtract the intersection of these two sets, or in other words, the probability that both events A and B can occur whenever we're finding the probability that event A or B would occur. So for instance, let's suppose that we have thrown 2 dice. The probability that we would get a sum of 7 or 11 would just be the probability that we'd get a sum of 7 plus the probability that we'd get a sum of 11, since the two events cannot occur at the same time. The number of ways that we could get a sum of 7 would be to throw a 1 and a 6, a 6 and a 1, a 5 and a 2, a 2 and a 5, a 4 and a 3, a 3 and a 4. The number of ways to get a sum of 11 would be a 6 and a 5 or a 5 and a 6. So this probability of getting a sum of 7 would be 6 out of 36, and the probability of getting a sum of 11 would be 2 out of 36. So we'd have 8 out of 36, which we could reduce to 2 out of 9. The probability of a certain event is always equal to 1. For instance, if I'm going to throw 1 dice, the probability that I would get a number less than 7 would be equal to 1. It is 100% certain that I'm going to get a number less than 7 since all of the outcomes on the dice are just 1 through 6. So in other words, there are 6 favorable outcomes divided by 6 equally likely outcomes, which would just be equal to 1. The probability of an impossible event is 0. For instance, if I want to find the probability that I would get a number greater than 7 when I throw a dice, then I would have 0 favorable outcomes out of 6 equally likely outcomes, which would give me a probability of 0. Complementary events are events that sum to 1. Their probabilities sum to 1. For instance, if I wanted to find the probability that I would throw a number less than or equal to 5, that would be the same as 1 minus the probability that I would throw a 6, where x is equal to the number of spots that shows up. In other words, a number less than or equal to 5, well, there are 5 sides of a dice whose spots are less than or equal to 5, so that would be 5 out of 6. But I could also find that by finding 1 minus the probability that I would get a 6. 1 minus 1/6, which is 5/6. Now the way we write this for complementary events a lot of times is we would have event E and then not E, and putting a bar above it or sometimes a little tick mark to indicate a prime would indicate complementary events. But in either case, the probability that event E will not occur is equal to 1 minus the probability that event E will occur. Another way to think about this is if there is a 40% chance that it's going to rain, then there is a 60% chance that it won't. Whenever we see the word and, we need to think the operation multiply. So this brings up the multiplication rule. The probability that event A and B would occur would be equal to the probability that event A would occur times the probability that event B would occur given A has occurred. And this little vertical line here reads given. So for instance, let's suppose that we're going to draw 2 cards from a standard deck without replacement. Now what I'm going to do is I'm going to make a little tree diagram that is going to show how this experiment will play out. The first branches of our tree will be the first draw of the card. Now, let's suppose that I want to find the probability that I would get 2 hearts. Okay, then on my first draw, I could either get a heart or not get a heart. Now the probability that I would get a heart on my first draw would be 13 out of 52, since there are 13 hearts and 52 cards that have an equal probability of being selected. The probability that I would not get a heart would be 39 out of 52. Now, on with the second draw. After getting a heart, I might get another heart, or I might not get a heart. Or, after not getting a heart, I might get a heart or not get a heart. Now I'm drawing two cards without replacement. So the probability that I would get a heart, given I got a heart on the first draw, would be 12 out of 51. Because if I got a heart, there's one less heart, and there's one less card because I did not put it back. The probability that I would not get a heart, given I did get a heart on the first draw, would be 39 out of 51. 51 cards left, 39 of them are still not hearts. The probability that I would get a heart, given I didn't get a heart, would be 13 out of 51. And the probability that I would not get a heart, given I did not get a heart on the first draw, would be 38 out of 51. Now the probability that I would get two hearts can be read the probability of getting a heart and a heart. So we're thinking multiply since we see the word and. And by following down this formula, we'd have the probability that I'd get a heart times the probability that I would get a heart given I got a heart on the first draw, which would give me the probability that I'd get a heart is 13 out of 52 times the probability that I would get a heart on the second draw given I got a heart on the first draw. That would be 12 out of 51. This can be reduced. 13 and 52 would give me 1/4. 12 is 3 times 4. 51 is 17 times 3. The 4s would cancel, the 3s would cancel, and I would wind up with 1/17. This notation, the probability that event B would occur given A has occurred, is called a conditional probability.